welcome back, ladies and gentlemen. We're looking at section 4.7 now, which is all about inverse trig functions. We're going to be determining the value of inverse trig functions based on a unit circle concept and solving problems using inverse trig functions. Okay, now a question I want to get this ball rolling with is using at least the first quadrant, which quadrants do you need to find all possible values of sine? Okay, well, I said it already, first quadrant, and honestly I'm just going with the first quadrant because first quadrant's so nice and all the coordinates are positive and everybody's happy and cheerful there. Alright, well, since sine is the y-coordinate, if I go the first quadrant, sine starts about 0 about right here, and goes through the various values until reaching a maximum of 1 right there. Well, if I continue through the second quadrant, I start just basically counting back down to 0, so that doesn't give me anything new, so it doesn't really do me much good. If I go to the third quadrant, yeah, sure enough, I have 0 here, and I go all the way down to -1 there. But it's a little awkward having the first quadrant and then the third quadrant being separate. Fortunately, if we come over here to the fourth quadrant, okay, 0 is here, and again, I can take my y values and start counting down and get all the various different y values possible until I get down to the -1 there. So basically, putting the fourth quadrant with the first quadrant, I get a complete span that covers every single possible y value. So as an answer here, we get quadrant 4 and quadrant 1 as our happy shiny place that covers everything we need to cover with sine. Okay, basically what that's important is then I can get any value of sine I want based on one of these angles here. And so that's kind of where the inverse is going to come from. Let's take a look at sine and, at cosine and tangent and explore this a little bit further. Okay, so looking at cosine now, same thing. I want to guarantee myself the first quadrant because my first quadrant is just kind of convenient to have. Alright, now cosine is the x-coordinate, so here my x-coordinate is 1, and over here I'm going to count all the way back until I get to 0. Okay, well now if cosine, I go in now the second quadrant, notice my x values again, now they actually start going from negatives. So I get negative little tiny decimals, and eventually all those negative values make it up to a -1. And basically first and second, that sounds pretty good to me. Okay, again, I could go with the third quadrant here to get all my negative cosine values, but again, I have the awkward situation of first and third quadrant, which, continuity-wise, that just kind of seems weird. I can't use the fourth quadrant with cosine because all of my cosine values here are positive and just be redundant. So again, to get every possible cosine value through one angle or another, I can stick to the first and second quadrants and get the job done. Coming over to tangent, again, guaranteeing myself the first quadrant. I feel happy about that. Okay, again, tangent of 0 is 0, and I cycle through here. Now remember, tangent is 1 right at the 45 degree or pi/4 mark, and as I get it to 90, it's actually undefined. So a little kind of a weird thing here is if I go to the second quadrant, yeah, I do get the kind of negative tangent value that I'm looking for, and I get all the way back down to 0 here, but I do have this discontinuity, this break in the graph there. So that is something that kind of doesn't sit well with me. So basically what I would do is, if I kind of mimic what we did with sine, and come down here into the fourth quadrant, okay, again we have 0, and then we go all the way to -1, and then we get starting to get those large values that are negative values here, as opposed to the large positive values here, and eventually we make our way all the way through with the rest of the fourth quadrant until we reach an undefined value there. But now we basically have negative infinity all the way through -1, all the way through 0, all the way up to positive infinity by doing basically what we did with sine, going through quadrants 4 and 1. So tangent is quadrant 4, that's actually a 4 right there, believe it or not, and quadrant 1, and I forgot to write it a second ago, but for cosine we can actually stick with quadrants 1 and 2. Alright, so by doing those various quadrants of the different trig functions, we cover everything that we need to cover as far as the possible values that they can be. That whole little discussion right there leads us to basically where the various trig functions are defined. Notice we're going to stick with the basic SOHCAHTOA ones and not worry about inverse cosecants and stuff like that, because quite honestly, anytime you have one of these things, you could always do a reciprocal to get back one of the primary 3, so there's not a great need to worry about the other 3. So we're going to stick with SOHCAHTOA and ignore the reciprocals for this concept here. Alright, so anyway, okay, the inverse sine, remember that worked in quadrants 4 and 1, and I do the same in that order because if we think about where this thing is defined, it's defined in the interval And again, remember we can include the endpoint there, wink wink nudge nudge, that's going to come in handy. Negative pi over 2 all the way to pi over 2, and that covered every single possible y value that we could have for sine. Alright, and then for cosine, again, cosine was the x value, and in order to cover every possibility for cosine, we basically started the first quadrant at 0 and wrapped our way around all the way until we hit pi, and again we included pi as well. Okay, again, I'm making a point of that because when we do tangent, okay, inverse tangent, well, we did pretty much what we did with sine, but because we had undefined values, basically at the negative pi over 2 and positive pi over 2, if we're going to write the interval, we actually have to discount the endpoints, if you will, and that gives us negative pi over 2 to positive pi over 2, but we're excluding those two exact values in order to kind of avoid the undefined values that we had there. Okay, a little notation thing here. The inverse sign that you're used to, because you're used to that button on the calculator, can be alternately written as arc sine of x, which is actually probably a better way to say it, because arc sine is basically, when we're doing this, we're basically asking ourselves, I want to know the arc whose sine is x. And if we do a few of these problems, it'll probably make a little more sense there. But then the same thing is true for cosine and tangent. We could use the arc word in front of the trig function to mean the same thing as the inverse. I'm guessing the calculator uses that because it's shorter to write above one of your buttons, as opposed to writing this 6-letter thing. You can just write that, it's a little bit quicker to do. Okay, so let's put this in action a little bit. Okay, so let's do the arc sine of -1, which again means I want to know the arc whose sine is -1. We're going to do this all in radians, so just expect it. Hopefully you've noticed all the pi's so far, so hopefully this was not a shock. Okay, but anyway, I want to know the arc whose sine is -1. So first of all, I want to think, hey, where the heck am I defined for sine? And again, I'm defined from negative pi over 2 all the way up to positive pi over 2. Okay, so basically I'm looking along this red arc and deciding where sine is going to be -1. Well, of course, sine is my y-coordinate, so I know, basically I'm asking myself, hey, where's my y-coordinate -1 on the unit circle? And sure enough, it's down here. Okay, now remember where it was defined. It was defined from negative pi over 2 to positive pi over 2, and this just happens to be one of those endpoints, negative pi over 2. Okay, if you want to lose points, then what you give as an answer here is going to be 3 pi over 2. Okay, so expressly this is not 3 over pi over 2, it is negative pi over 2 because of the way this thing's defined. So make sure you always give me an answer that ranges from negative pi over 2 to positive pi over 2 for sine. Don't give me anything that's coterminal, because technically that's incorrect. Okay, moving along to cosine. If I want the cosine, inverse cosine that is, of -1/2, again, I want to know the arc whose cosine is -1/2. So I ask myself again, hey, where's cosine defined? And it's defined from 0 all the way over to pi. So again, this is where I'm looking. Okay, so you got this guy with his headphones on here, and we got to figure out where we're at the -1/2. Okay, just for the fun of it, I'm going to change colors because this one takes a little bit more work. Alright, so cosine again is the x-coordinate. I want the x-coordinates to be -1/2, so again, -1/2 always pairs up with a √3 over 2, so I'll draw kind of my exaggerated triangle right here, and hopefully from there it's evident that I have a 60-degree reference angle, so the angle from here to here that gives me the cosine of -1/2 that I'm looking for versus the √3 over 2 right there. Okay, that's going to be a 2 pi over 3. So again, I'm asking for arcs, so make sure when you're doing these inverse things, your final answer is always some angle measure, and do expressly make sure that it fits in whatever defined range of values that you're talking about. Okay, I'd like to do a couple more of these involving tangent, because tangent tends to be ones that kind of mess people up a little bit. So again, arc whose tangent is √3. Okay, so again, tangent, I'm going from positive pi over 2 to negative pi over 2, so again I'm looking through the basically first and fourth quadrants, just like with sine. Alright, now I need to come up with a √3. Well, first of all, I'm looking for a positive √3, so, okay, basically I know I'm dealing the first quadrant, not the fourth. Alright, so I've got that. Now again, I know this has got to be my y over my x, and if I've got a √3, it probably means I've got a √3 over 2 involved. And if I stack up my fractions like this, notice the 2's would cancel, and then I know I've got the root 3 over 1, which gives me the root 3 I'm looking for. A little bit of trial and error is necessary sometimes. I know if I'm looking at the root 3 over 3, sometimes I have to play around with it and piece it together, but I think that's a pretty good way to do it. You should be able to do it fairly quickly. Okay, with that being said, remember this is my y over my x. So I know I've got my root 3 over 2 has got to be my y, and my x has got to be the 1/2. So basically I'm looking at a triangle roughly like this, where there's my root 3 over 2, there's my 1/2, and hopefully by now you're like, yeah, get on with it, I know it's pi over 3. Alright, so there's that. Okay, in a similar fashion, if I have the arc whose tangent is 1, alright, okay, again, as soon as I'm dealing with tangent, I know first thing I do, I'm dealing with quadrants 1 and 4. Okay, but again, I'm positive again, so I know I'm still up in quadrant 1. And this is one that tends to make people's brains explode, because the ones you're usually thinking are at either pi over 2 or 0, but remember with tangent you're doing a ratio. So I had to do something divided by itself to get 1. Well, the only way to pull that off, of course, is have the exact same number. The only place that happens is with our root 2 over 2's, better known as the numbers you get from the 45-degree or pi over 4 angle. So there's a root 2 over 2, there's another one of those guys, and again that means that we've got an answer of pi over 4 in that situation. Alright, hopefully that made a little bit of sense. Of course, ask if it didn't. Okay, if you're being asked to evaluate something like this expression right here, now first of all that probably looks very, very scary. And well, maybe it is, but just pay attention to what Aunt Sally used to tell you about working from the inside out with your order of operations. Okay, so really I've got this big mess here, but first thing first, I'm just going to go for the inverse sine of 7/25. Okay, so what I'm going to try to do from here is construct myself a triangle that gives me that sort of arrangement of numbers. Okay, so first thing I'm going to do is draw myself a nice little x and y axis. That was a little bit on the tilted side, but hopefully you can cope. Alright, again, with my regular SOHCAHTOA inverse sine, I've got 7/25. So again, SOHCAHTOA tells me that's opposite over hypotenuse. So I know I've got to get myself a triangle. Let's change colors. Okay, my opposite side's got to be a 7, and then just to try to draw it to scale a little bit, 25 is pretty much a lot bigger than 7, so I'll draw 25. And hopefully you remember your Pythagorean triples, and that puts you to 24. Okay, one thing I forgot to mention is because I'm dealing with a positive value here, I knew I was in the first quadrant. If I'd had a negative 7/25, I know I'd been down here in the fourth quadrant. But alright, that being said, basically this now gives me an angle measure here. We can just call it theta for the sake of just having something to call it. And so now, basically what I've done is now what I really want to know what cosine of theta is. Alright, so there's my theta, and now again, just playing SOHCAHTOA with my cosine gives me 24 over 25. And so final answer is what I just said, 24 over 25. Okay, so moral of the story, use the kind of inside guy to draw yourself a triangle or do whatever the inside guy says to do, and then get that result and do the outside thing to that result, and that'll get you some kind of a final answer. Okay, hopefully that makes a little bit of sense. Okay, here's our assignment. Again, please take note of the red down there. Don't stop the video. 4.8 is included as well. Basically, 4.8 is going to be a section on word problem stuff, and there's just a couple things I need to point out, and I didn't think I'd go through the trouble making a complete extra video for it, so basically here it is. Okay, so for 4.8, I'm not going to do a whole separate objective because, quite honestly, it's just a bunch of word problems, so boom, whatever. Here we go. One of the things that's a little bit weird in this section is they use bearings, and they do them a couple different ways. The first way is just giving a single angle measure. The book likes to say that planes do this one way and boats do it the other, but whatever, it doesn't matter. You don't need to worry about what you're talking about, you just need to worry about how to interpret them. So anyway, if they're just giving a single angle measure as the bearing, or sometimes they even say heading, it means the same thing. Basically, north is a 0-degree angle. And then basically from whatever angle measure they give you, you just simply go in a clockwise direction. Okay, so for example here, if I have a 10-degree angle, alright, all that means is I kind of start out kind of due north, if you will, and then I just kind of want to bend in that direction however many degrees that is. So if I'm going on a heading or a bearing of 10 degrees, this is what it would look like. Okay, so basically it would kind of be an 80-degree angle based on what we're used to as far as our trig stuff, but when we're talking degrees and stuff, that's how we're going to work it. Okay, something like 270, so basically we don't need to stay acute. 270, of course, is starting north again, and then going 90 this way, 180, and then another 270 gets us over here. So, if you hear 270 degrees, that's basically due west. Alright, so again, just basically, this will always be something between 0 and 360. You won't see these as negatives. And just wrap yourself around clockwise as many degrees as it says to go. Alrighty, the second method is going to be, I have no better way of referring to it, so at least for now I'm going to say direction, angle, direction. But basically all it is you're always going to start on the first direction and bend toward the second. Okay, and that maybe sounds a little weird, but one thing that will always happen is it's always going to be either north or south first. And then you're going to have your angle, and it's always going to be acute, and then the other direction is going to be either east or west. So something like north 23 east would be very similar to the last one, where we're going to start due north, and then we're going to bend 23 degrees toward the east. Okay, east is of course to the right, so this would look something like a 23 degree angle coming off of this direction. So this one's actually fairly similar to that 10 degree angle we had a few seconds ago. Alright, something like south 75 degree west will definitely play a little bit differently. So I'll start out to the south, due south, and now I want to bend 75 degrees to the west, which is kind of like left. So again, starting due south, and if I go 75 degrees, that's most of the way toward that 90. And there's where the 75 degrees would be. And then so basically that's your heading, bearing, direction, whatever you want to call it, based off south 75 west. Okay, so those are how those work. Of course, if that didn't make a lot of sense, hit me up in class and I'll explain a little bit further. Alrighty, so then here's what the assignment for 4.8 is going to be. It's not a ton of problems, but again, they are word problems, so it does make it a little bit tricky sometimes. Hopefully some of them go really, really fast for you. And a few of the other ones make you think a little bit. But there it is. Good luck. I'll see you in class.